All right, so this is lecture 15, which is on the shape operator. Just a brief comment here. So we're considering some surface in R3. All right, so it's some kind of two-dimensional, in the sense explained in chapter 4. Right, there's some local bijections between R2 and this thing, and we want to understand what does it geometrically look like, right? So first things first, we're going to think about there being some normal vector field, and our surface we're going to call M, right? Now the normal vector field may be something like, so we want to think about a vector field which attaches a unit vector at each point, right? And that point is, well, the normal to the tangent space, right? So like if you were to envision the tangent space attached at that point, well then that tangent space has the green arrow as the normal, right? This tangent space has the green arrow as the normal, and so forth. And if this surface was curved, then the way these normals change from point to point would, tell you something about how the shape was curved. Like here's a better picture. So suppose you're looking at, this is the surface kind of looking at it. Here, I'll draw some like that, right? Here's a surface M. And, excuse me, here's the normal like this, right? And you can see, if you can envision it in your mind's eye, that as you go from point to point, the normal's direction is changing, right? And so the way that normal's direction is changing somehow is capturing the shape of the surface, right? That's the idea. Now, so to capture that notion, we study something called the shape operator. But before I even define it, I just want to give you a little lemma. And so here it is. If we study the, excuse me, the operator minus the, well, I don't even need the minus, forget the minus for a second here, scratch the minus. If we study the operator, the covariant derivative of v of the unit normal u, then this naturally defines a mapping from the tangent space P at M to the tangent space P at M. All right. Of course, let's see here. So we're sending the mapping to the covariant derivative in the v direction of the unit vector field u. Okay, that's the mapping, to be clear. Now, the proof, so this is the little lemma. Proof of this lemma is pretty simple. Basically based on properties of the covariant derivative. First of all, you notice the unit vector field, right? So u dot u is equal to 1 because that's the length. But then if you look at the vector field v acting on u dot u, of course the derivation acting on a constant is 0. But on the other hand, it's also, what is it? Well, by properties of the covariant derivative, it's a covariant derivative of v on u dot u plus the covariant, plus u times the dot of the covariant derivative in the v direction of u. All right. And so there you have it. The covariant derivative in the v direction of u dotted with u is equal to 0. But that tells me that the covariant derivative of v of u is an element of the tangent space to P at M, right? If I'm, again, considering this at the point P. Because, of course, the tangent space to P at M, the perp of that, right, is given by the span of the unit normal at that point, right? Or if you want me to be all pedantic about it, we could say this. We could say the tangent space to P of R3 is the direct sum of the tangent space P at M and the span of the unit vector. Or if you like, in more geometric terms, it's the span, it's the direct sum decomposition of the tangent space and the normal line. And as you can see, this guy is in fact perpendicular. So all of this being said, this allows us to define the shape operator as follows. Definition If P is an element of M, then for each V in the tangent space P to M, let the shape operator at the point P acting on V be equal to minus the covariant derivative in the V direction of U. Okay. And I guess just to be super annoying about it, let me say, of course, that's at the point P. All right. Anyway, this SP, which as I've just proved is a mapping from TPM to TPM, is the so-called shape operator. I can't spell, at P. All right. Now, of course, you can do that at each point in the surface, and in so doing, you have a function, right, from the tangent space P to tangent space P. So what else can we say? What kind of operator is this? Well, it's our favorite kind. It's a linear operator, which ultimately is going to allow us to, do linear algebra, which of course is something we like to do. Oh, I guess I should state that. So here's little proposition. Sorry, my notes are. It's not in my notes yet. It's just later. How do I do this later? Sorry, I know it's a linear operator, but I've lost track of something here. Like I feel like I'm getting out of order. No, it just okay. So proposition: the shape operator at the point P from TPM to TPM is a linear transformation. That seems like it's important enough to get its own proposition. Now, how do you prove such a thing? Well, I suppose depends on how we want to do the calculation for the covariant derivative. So let's see here, SP, let's say AV plus BW, where V and W are vectors at P. Well, that would be the covariant minus the covariant derivative, right? AV plus BW on U, right? And of course, that is a minus covariant derivative V U plus B minus minus B covariant derivative W in direction WU times B using the properties of the covariant derivative. And of course, well, there you have it. That's A times SP of V plus B times SP of W. And so there that goes to prove that the shape operator is a linear transformation. It's just from properties of the covariant derivative. Nothing too shocking there. All right. So some examples of the shape operator. But actually that's a huge thing, because that means that we can use linear algebra to study the shape operator, as we will do in many cases in this section. All right, so let's see here. Try not to choose a color. Well, here's a very boring choice, but it'll work. Example 1. How about the sphere? In particular, the set of points such that the length of the point is equal to r. In other words, a sphere of radius r centered at the origin. Well, if you kind of picture that, it's not hard to see that if this is the vector, this vector, I sometimes would call it r vector in like physics. Well, r vector would be what? It's just the sum I equals 1 to 3 of x upper I, u lower I rather, right? It's just a plain old position vector. And well, it's not hard to see that the unit vector geometrically is just, points in the same direction as that. Like this, right? That's like u. And so the formula for then u, you just have to rescale the length of r so that it has length 1, right? But if this position vector is on the sphere, well, the length of r, of course, is just equal to little r. Sorry, not the best choice of notation here. Well, too late. Anyway, so u is equal to 1 over r, that's a constant, all right? Sum I equals 1 to 3, x upper I ui. All right. So you can calculate the covariant derivative then with respect to this normal vector field, right? The covariant derivative in the v direction of u is going to be what? Well, there are two ways to calculate the covariant derivative, right? The one way we could calculate the covariant derivative, like covariant derivative of v of, let's say, the vector field z, we could do like the sum I equals 1, 2, 3 of v acting on the component, the ith component function ui like that, or that was the first method. The second method to calculate would be that the covariant derivative of v of z, what you do is you just find the vector field, which has v as its tangent vector at 0. You take the vector field, the curve, rather, alpha that has alpha prime of 0 being v, and then you just take, z composed with alpha, basically, and prime of 0. That was the other way to calculate the covariant derivative. So we'll use both of those, but we're going to use method 1 for example 1. So what we do here, in this case, so the unit vector, the unit normal is playing the role of z here, and the component function, so this is going to be sum I equals 1 to 3 of what? Well, let's see here. So we got v acting on what? Well, the zi is xi over r is a constant, right? And then ui. But the constant pulls out, right? And you're just left with sum over I, 1 over r, v of xi, ui. Hey, but what's that? This, if you pull the r outside the summation, this just gives you v again, because that's just the ith component of v. And so you're just left with v over r, in fact. So, therefore, the shape operator at any point p on the sphere acting on v, it just gives me minus v divided by r. And there you go. And that kind of makes sense, because the way the shape operator works on the sphere, it's the same independent of which point you're on the sphere. And that makes sense because the sphere has the same shape, although I'm just using that word heuristically right now, but the sphere has the same shape at each point, right? So obviously this is a kind of special example, but an important example. Another example, which is equally easy, maybe this example is too easy, I don't know. Let's see here. This is the question you'd love to have on your test. Calculate the shape operator for a plane. So if P is a plane in R3, then the unit normal is just the constant vector field AU1 plus BU2 plus CU3, and of course the covariant derivative of V acting on U is just equal to 0 because U is a constant. Daniel, what are you doing? No, not while I'm doing the... You can go play somewhere else right now. What? Go play somewhere else. I'm doing this here.
Ask Jacob if he wants to play.
Yeah, you can ask Jacob if he wants to play. That's fine.
Okay.
All right. Sorry. Distracted.
I don't think we should do it in our house because Matthew's sleeping.
That's right. You can do it in the backyard. Or you can play in his house.
I'll ask him if he wants to.
Okay. Again, sorry. So the covariant derivative of u in the v direction is 0, right? So that tells you that the shape operator at any point P on the plane is equal to 0, all right? So a plane has shape operator, which is just trivial. Another example, example 3, the right circular cylinder, C such that x squared plus y squared is equal to r squared, right? This is the right circular cylinder in R3, and if I were to draw a picture of it, let's see here. Of course, you can draw these curves along the cylinder, right? The vertical curves, I think, are called rulings. They run parallel to the axis of the cylinder, and then the horizontal ones are cross sections, right? And so there are two sorts of vector fields you might think about. If I pick this point P, let's say, then I can talk about this one being, say, E1, and I can talk about the blue one here being E2. All right, those are perpendicular, and then U, I can't draw worth much. I mean, it's there. The U is coming out. I mean, it's U is like this over here. I can draw it over here, right? I guess it kind of. No, I'm not gonna try to draw it. Anyway, so you can see though that if you think about U, it doesn't change as you go up and down these rulings, right? Whereas whereas the unit vector is changing around the circles, right? So here's here's my favorite cylinder. So here's the unit normal. As you can see, it is changing direction as you go around the circles, right? If you go around a circle, the thing changes direction. But if you go up and down the ruling, it's just parallel translating. It's just moving its point of application, but the vector part of the U isn't changing. Now, so it goes to stand. It stands to reason geometrically, right? If we understand covariant differentiation a little bit, what it means geometrically, then you can see that the shape operator at any point P acting on the vector field E1 is going to be equal to 0, because that's minus the covariant derivative along E1 of the unit. The unit normal doesn't change along the E1 direction. Whereas the shape operator acting on E2 we expect is not equal to 0. And on the basis of the similarity between like a great circle on the sphere and a circle on the cylinder, we kind of expect that that should be minus E2 over R, where R is the radius of the cylinder, right? Because it's just like the sphere. Now, we can calculate that directly, and I'll do that. Let's see here. Oops. What am I doing? What am I doing? Sorry, I gotta get my papers in order here. All right. So to calculate that directly, come on. Here we go. I suppose I need, well, I guess I need the formula for U, right? So the unit normal I can write in terms of the angle, the standard angle. I could write it that way. U is equal to what? It's well, it's I would call it R hat in calculus 3, but just to get to the point here, cosine theta U1 plus sine theta U2. As you can see, there's no U3 dependence, because it's got it points out the z-axis is the axis of the cylinder here. So there's the unit normal. And let's see here. What are the formulas for E1 and E2? Well, and again, I'm arguing geometrically here. E1 is just U3. And you're like, well, if you're arguing geometrically, why do you even bother with these calculations? That maybe is a good question. E2 minus sine theta U1 plus cosine theta U2. You may recognize this as theta hat, right? It's the unit vector in direction of increasing standard angle. And so the covariant derivative, right, in the E1 direction of U is what? Excuse me. It is, well, you know, I don't know if I can find. I'll write it out. It's u3 acting on the first component function cosine theta u1 and plus u3 acting on sine theta u2. Of course, there is no z dependence. There is no z dependence on the standard angle, so these guys drop to 0, and you're just left with 0 as we claimed, right? So shape operator gives me back acting on e1 gives me 0. All right. On the other hand, the covariant derivative in the e2 direction acting on u would give me what? Well, so e2, all right, is minus sine theta u1 plus cosine theta u2 that first acts on cosine theta, but let's write cosine theta as a function of x, y, and z, all right? So cosine theta as a function of x, y, and z is just x over r here because we're on the cylinder, all right? So cosine theta I'm going to write as x over r. That's my cosine theta. And then, of course, all of that multiplies by u2. And then same thing again. And then I have to act on sine theta, and then I multiply by. Oh, did I put u2 here? I meant u1 because that's the first component function of the unit normal. So that should have been a 1. Sorry about that. And I should put u2 here. I'm using formula 1 for the covariant derivative I wrote back on page 2 of this lecture. But anyway, sine theta is y over r. All right. Now, because we're on the cylinder, and of course, there is no. Now, u1 and u2 are partial x and partial y, right? So this just drops to 0. There's no x dependence on this one, so that drops to 0. And on the other hand, we get minus sine theta over r u1, and then over here I get plus cosine theta over r on u2. But what is that? Well, that's exactly e2, right, over r. So therefore, the shape operator at the point P acting on e2 is equal to minus e2 over r, just as we claimed by analogy. Excuse me. And now there you have it. Now, probably our next example is a little bit. I've lost my. Oh, here it is. Lost my cap. The next example is the saddle surface. Saddle surface I have trouble drawing, but I'll take a shot at it. So here's one way to draw it. So the thing about the saddle surface, right, is you've got one direction, and we're gonna take a long, well, hopefully not too long, little look at the point P. Now here, the saddle surface, the equation of it, right, is z equals to, it is a graph, all right, so z equals to xy, all right. Make sure every once in a while I forget to zoom the camera where it needs to be. Anyway, page 4. So we're looking at the point P being the origin, all right? So P equal to 0, 0, 0 is what we're going to look at. And so at that point, right, there's two really interesting curves, I suppose. Well, I mean, there's lots of interesting curves, but, you know, our unit normal is going to look like that, right? And so on the one hand, we've got this curve that rises up away from the unit normal like that, right? We've got that curve. But on the other hand, you have this other curve like this, right? Which drops down on either side, right? And so you could think of the surface as bending up towards the normal, right, as you go along this blue curve, whereas the surface is bending away from the normal if you trace out the red curve, which I'll be so foolish as to try to draw back there. I'm going to regret that. Now, so let's think about E1 and E2. Now, those two curves I just drew are actually not the coordinate axes. The coordinate axes, if I think about the coordinate axes, they're actually, oh, goodness gracious, they're something like exactly between these. So something like this might be the, oh goodness gracious, x-axis or y-axis, I don't know. And then the other one, I'm not, but inside this, you know, one of the, if you look at this, x equals to 0 gives you what? If you put x equal to 0, you get z equals to 0, right? If you put y equals to 0, you get z equals to 0. Those are on this surface. So the xy, let's see here, if z goes that way, I guess I should make this x, and I guess I should make this y. So if you look at this, you know, this surface, it does have the x and y coordinate axes are actually in the surface, right? And so for the purpose of this example, we're going to say that like E1 is along, you know, this has the E1 direction and this is the E2 direction, right? And so, and this is harder for me to see, but he says U bends towards E2 if we travel in the E2 direction from P, is that right? Away from E1. Alright, so if I can imagine, I'm not very good at imagining this, but the unit normal, and then it kind of would drift forward like that. So if I go in the E1 direction, it's, I think I have a typo in my notes. I think it's looks like as it's going in the, as you go in the E1 direction, it looks like the normal's kind of bending forward like that, which means it's moving opposite E2. And I think this similar thing is sort of true for E2. If you go in the E2 direction, it actually bends in like the E1 direction the unit normal does, something like that. Well, you know, fortunately, we don't have to rely on pictures anymore. We can actually calculate these things if we're so bold. This is actually a great opportunity to use the curve definition of the covariant derivative in this example. We're going to do that. That will work out better for us. I tried calculating directly. Oh my goodness, that was, well, I'm sure you could do it, but it was unpleasant. So obviously there's a patch on this. The patch that I would use would be x of, well, let's say xy, and that patch would look like, well, x, y, and then xy, right? And let's see here, a short calculation will show you that the unit normal, you can get that from calculating partial x cross partial x partial y. When you do that and you normalize that thing, what you get is 1 over the square root of x squared plus y squared plus 1 and minus y minus x 1. Now it's easy to check. It's easy enough to check that I must be right, because if you calculate partial derivatives of the patch, well, that's not hard, right? Like partial x is 1, 0, y. Partial x partial y, 0, 1, x, right? And if you take the dot product of partial x with this, you get minus y plus y, 0. And if you take the dot product of this and this, you get minus x plus x, which is 0. So this is in fact perpendicular, and as you can see, it's been normalized. So that must be indeed u. So who knew you had such an interesting formula? But there it is. All right. Now, so all right, I want to calculate the covariant derivative let's say I want to calculate the covariant derivative so now again p, I'm still fixing p to be the origin, all right? So calculate the covariant derivative at p being the origin of E1. So I need to find alpha such that alpha prime of 0 is equal to E1. And I also, of course, want alpha to be a curve on M. All right. Now, so I think it's not too hard to do. Just think about it for a second. You can use alpha of t equal to what? Well, how about t0, 0 seems like a good choice, right? That thing just sits on the y equal to 0, z equal to 0. Y equal to 0, z equal to 0. This is otherwise known as what? X-axis, right? By the way, x equal to 0, z equal to 0 is the y-axis. As awful as this surface is in some sense, it's actually very simple in the sense that it has both the x and y-axis, and that's kind of cool. Anyway, so as you can see, alpha prime of 0 is E1. And if I calculate u of alpha of t, that's, in other words, the unit normal vector field along this curve alpha, what do I get? Well, you just plug in x equals to t and y equal to z, and y and z both being 0. So plugging that back up in here gives me excuse me, 1 over the square root of t squared plus 1, and then 0 minus t, and then 1. All right. And let's see here. So you can then calculate that use of alpha as another notation for this. Use of alpha prime of 0 then is equal to excuse me, 0 minus 1, 0. A short calculation shows you that. It's not hard. Basically, when you differentiate this, you get a product rule, right? But the term which differentiates this normalization factor out here, it has a 2t or a t upstairs, and when you put in t equal to 0, this term drops out. So it just leaves you this times the derivative of that, which of course is 0 minus 1, 0, because 1 differentiates to 0. Plug in 0, that gets 1, and so out pops this. All right. Hey, but that's exactly minus E2, right? So being that the covariant derivative at E1 of u with a minus, all right, that's the shape operator at the origin acting on E1 is by definition this, right? But by the way, it's also u alpha prime of 0 with alpha being so constructed, and as you can see, that's minus E2. All right. Then, excuse me. Trust me when I tell you, trying to calculate this directly from the Cartesian coordinate formulas is unpleasant. So the curve-based definition for the covariant derivative here is really, following Chef Ramsay, I would say it's the hero. But anyway, that probably means nothing to most of you. All right, alpha of t, on the other hand, equal to 0, t0 would put me on the y-axis, right? Y is free, x and z are fixed to be 0. When you calculate u composed with alpha of t this time, we get let's see here, 1 over the square root of 1 plus t squared, and then minus t, 0, and then 1. And short calculation, very similar to the one we just did, or almost did, alpha prime of 0 ends up being minus 1, 0, 0. And that goes to show you that, I've lost a sign up in my previous step. Minus, that was, there's a minus here, right? Which makes this a plus, plus, plus. And likewise here, so the shape operator at the origin, P, acting on E2, gives you minus E1, minus a minus E1, which is just E1. And so there you have it. It's actually very simple in some sense, right? the way the shape operator acts here. The shape operator acting on E1 gives you E2. The shape operator acting on E2 gives you E1. All right. So if you stop and take a look back at the different examples we've studied so far, it's probably worth writing the matrix of the shape operator with respect to the vector fields we chose, or the vectors we chose at each tangent space, right? So actually, so example 1 was the sphere, right? Example 2 was the cylinder. I can't spell cylinder. Example 3 was that? Oh, I'm an idiot. It wasn't even the cylinder. What was it? Example 2 was the plane. Stooge. Plane. And example 3 was the cylinder. Hopefully I've learned to spell it by now. I don't know. Example 4, saddle. Right? And so just to recap what we found was SP acting on V was just equal to, what was it? So soon I forget. Minus V over R. For the plane, we had that the shape operator at any point P was just 0. For the cylinder, we had that the shape operator at the point P acting on E1 was 0, but the shape operator at any point P acting on E2 was minus E2 over R. And finally, for the saddle, we had the shape operator acting on E1 was E2, and the shape operator acting on E2 was E1. So now we didn't even have a choice of basis in some sense here, but so if you think about, fix a point P, think about the, so let's say the matrix for the shape operator, which again is a linear transformation from TPM to TPM, was thus. So let's see here. I hope the notation is clear enough what it means. I mean, it doesn't matter what choice you choose, what choice of basis you choose, the matrix for this, the shape operator's matrix. The sphere's shape operator matrix was just this diagonal matrix with minus 1 over R, minus 1 over R. It doesn't really matter what you choose for basis. Similarly, the plane doesn't really matter which basis you choose for the plane. The matrix is easy enough to understand. The cylinder, the matrix for the shape operator would be like 0 minus 1 over R. And the saddle, the shape operator, would have matrix, let's see here. So, and I'm using the basis E1, E2 for these last two examples, obviously. So E1 goes to E2, that makes 0, 1 the first column. E2 goes to E1, that makes 1, 0 the second column. All right, and well, there you have it. Those are the matrix, the matrices for our 4 examples. Now, just looking ahead a bit, we're soon going to learn that the determinant of the shape operator is called the Gaussian curvature, and well, not the trace, but 1/2 the trace of the shape operator. I think it was 1/2. Yeah, 1/2 the trace of the shape operator is so-called mean curvature. So if you don't mind me putting this out of order, I hope you don't. If you do, it's too bad. This has K Gaussian curvature is the determinant of that matrix. And so the Gaussian curvature is 1 over R squared here. The Gaussian curvature for this is 0. The Gaussian curvature for that is 0. The Gaussian curvature for this is minus 1. So things with negative Gaussian curvature maybe are saddle-shaped. Things with positive Gaussian curvature maybe are something like a sphere. Things with 0 curvature could be a plane, but it could be something like a cylinder, which, I mean, say a cylinder has 0 curvature? Well, 0 Gaussian curvature, yes it does. Now the mean curvature 1/2 the trace of the shape operator's matrix. Well, let's see here. That would be, I guess, -1/r then, right? The mean curvature of this is 0. The mean curvature of this is -1/2r. And the mean curvature of this is 0. Okay, so surfaces with 0 mean curvature are called minimal. And that's explained, I guess, maybe later in O'Neill a little bit, although it's explained in great and interesting detail in terms of its connection to complex analysis if you look in Kuhnel. I think it's 3C, 3D, something like that. It's very, very interesting. Okay, now moving along here. So in the next part of the lecture, I'm going to explain a little bit more about the shape operator. We're going to talk about normal curvature, and basically we're moving on to section 5.2 next. I'm going to stop here and start again, so thanks.